Imagine your boss pulling you into his office at 9 a.m. Overnight, the company has lost 100,000 euros. A bug in your team service turned the VIP offer into a site-wide giveaway. That terrifying experience became my reality after a communication failure between our brand new microservices. And recently, two of my coaching clients ran into similar problems. Luckily, there is a solution. And in this video, I will tell you how my team rediscovered a pattern from the 80s that turned our fragile system into a resilient one. Join me and you will never have to wake up at 2 a.m. to PagerDuty like I had to. For weeks. But how did we end up with fragile microservices in the first place? Well, our problem started much earlier with the legacy monolith. Multiple dev teams were shipping features into this absolutely massive system. Meanwhile, ops was drowning in alerts, firefighting after every single release. Just like many other teams, we ended up with an unmaintainable mountain of spaghetti and an ops team that tried to stop every new release. So, like every other team with a legacy monolith, we introduced microservices. And it was great! Teams had their own services, deploys were happening faster, and ops finally got some sleep. Our team owned the email automation system. Users could design workflows, and we were supposed to make sure that they ran smoothly. Supposed to. For example, they may want to send an email, wait 2 days, and if their VIP customers don't respond, send them a big discount. Except, the segmentation failed. As for the discount meant for VIPs, literally everyone got it. It would be easy to blame the segmentation team. After all, it's their service that failed. But that wouldn't solve the problem. Here is something I learned from my ski instructor. If you are skiing, you're going to fall. It's not a question of if, rather when. But if you know how to fall safely, you're not going to injure yourself. And that's the same with microservices. If you have a lot of them calling each other, some of them will sometimes fail. And that's okay if you know how to handle it. So in this video, I will show you how to fail gracefully with microservices. First, I will take you on a journey of how we try to solve the problem, so you understand why the different obvious solutions don't work. Next, I will show you the correct solution at the high level. And finally, we are going to dig deeper into the implementation details, so you can apply this pattern without the mistakes that we made. Let's go. Imagine you are booking a rental car online. The system needs to check availability, reserve the car, and assign it to you. All of these could be separate queries in the database. But what if something fails? Now we have a reserved car with no driver assigned. That's not great, is it? That is why we use database transactions. If something goes wrong, the database simply rolls back to the last consistent state. That's a pretty solid solution. Until it isn't. Reserving a single car is one thing. But what if you are planning an entire ski trip? Now you need a flight, a rental car, a hotel, and a ski pass. Each of these are managed by different companies. Each has its own system, its own database, and its own rules. Good luck starting a transaction for that. And even if you could, long-lasting transactions mean long-lasting logs. You'd end up with a massive performance issue. So what did we do instead? The responsible thing, obviously. We definitely did not just ignore failures, did we? Unfortunately, we did. Each action was a transaction within the relevant microservice, but our system just assumed that every action would complete as expected. What could possibly go wrong, right? When we realized that this is, well, pretty dumb, we added exceptions when the operation failed. This at least resulted in PagerDuty alerts, so we could recover manually. And result in alerts it did. But fear not, we had a solution. Let's catch the exception and retry a few times. Seems reasonable, right? Except, if a service was down due to an overload, slamming it with 100 retries didn't exactly help. It was like trying to fix a traffic jam by honking louder. What were we thinking? But the next solution was pretty close to the right one. Instead of immediately retrying, we waited, doubling the time between each attempt. This already worked surprisingly well, but there were still issues. On one hand, we kept the process running, which put unnecessary load on the machines. And if the process crashed, the entire workflow would stop. On the other hand, if a request could never be successful, we would still be stuck with an inconsistent state. It was at this point when I discovered two-phase commit. But we quickly realized that it had similar issues. In two-phase commit, first, all services are asked to open a transaction and perform their actions. After each service confirms success, all of them are notified to commit the transaction. So what's the problem with this? Imagine you are at a restaurant with a big group. First, everyone orders one by one. Then the waiter goes away and your meals get prepared. So far, so good. But if one dish takes forever to complete, everyone just sits there hungry. By the time you get your meals, it's cold and yucky, and there is a queue outside because you were holding the table all that time. And that is exactly the problem with two-phase commit. It's just with data tables and not dining tables. Am I taking that metaphor too far? I don't know. The transactions holding logs completely kills the system's performance. But here is the good news. Even though you may not realize, by now we basically have all the pieces. We just have one more thing we need to understand. You see, at first we ignored failures, but after that we made the opposite mistake. We became obsessed with trying to reproduce proper ACID transactions. What are ACID transactions, you ask? A stands for atomicity. Either everything is completed or nothing is. You either have your plane ticket, car rental, hotel room, and ski pass, or you have none of them. C stands for consistency. The end result shouldn't contradict known rules. A single hotel room should only be booked for one person. If two people somehow book the same room, that's an inconsistent state. I stands for isolation. Every action taken within a transaction is visible only to that transaction. If I'm organizing a ski trip and I have only booked my flight and car rental, no one else should see that those are taken until my entire transaction is complete. Finally, D stands for durability. Once the transaction is done, it's done. No power outage, database crash, or magnetic storm can undo it. And here is the crucial insight my coach at the time shared with me. If you can't make all four work, you need to know which one to let go of. So which one would you choose? Let us know in the comments. At first, it seems like we need all four, but here's the problem. Trying to build a perfect solution across multiple services kills performance and stability. So instead of forcing ACID transactions across services, we have to think differently. But we don't throw out ACID entirely. Instead, we break the process into a sequence of actions, each of which is still an ACID transaction on its own. And to demonstrate how that works, it's time for me to book my next ski trip. The easy case is when everything goes smoothly. I make 4 calls, book my flight, reserve my car, secure my hotel, and buy my ski pass. Of course, life doesn't always go as planned. This time when I called the hotel, it was fully booked. Now I have to course correct. I already have a plane ticket and a car reservation. It would be tempting to just find another hotel, but that requires making decisions. Our algorithm cannot rely on human decision making, so instead we need to roll back the previous steps. Besides, I hate change. I want to stay at my favorite hotel, so I guess I will have to call them back. The easiest solution is to cancel my car reservation and my plane ticket. I can't reach the airline right now. I will have to call them later. What you have just seen in action is the Saga pattern. Formally, the Saga is a sequence of independent actions with idempotent compensating actions. That's a mouthful. Let's break it down. Our actions were booking a flight, renting a car, reserving a hotel, and buying a ski pass. They were independent. Each one could be completed or cancelled without affecting the others. But what are compensating actions? In this case, it was simply cancelling the reservations. Or compensating actions don't necessarily undo a step. They just ensure the system ends up in a state that is acceptable, even if it's not exactly as if nothing has happened. For example, the airline might not refund the full ticket price. They could charge me a small fee or only allow me to use the amount for a future flight. As long as the difference from never booking in the first place is minimal, that's an acceptable trade-off. But there is one more thing that we need to get right: retries. And that's where idempotency comes into the picture. An operation is idempotent when applying it multiple times has the same effect as applying it once. But why is that important? Let's suppose the cancellation email for my flight didn't arrive. Now I might worry that something went wrong. So I call the airline again to cancel my reservation. Since I'm canceling by reservation ID, the worst that can happen is an annoyed administrator telling me it's already cancelled. But that's a small price to pay to ensure I'm not being charged for something that I don't need. The key idea, just like with compensating actions, is that repeating the action shouldn't produce a significantly different result from doing it once. That way we can safely retry until we can be sure that the action was successful. Let's look at some more examples and see if you can guess which ones are idempotent. Is booking a hotel room idempotent? If you guessed no, you were correct, since doing that twice will result in exactly twice as many rooms as I can possibly sleep in at the same time. But what if I try to book a specific hotel room for a specific night? That happens to be fine, since the worst that can happen is having to deal with an annoyed receptionist. again. To sum it up, the Saga pattern replaces strict ACID transactions with a sequence of independent actions. If something goes wrong, we compensate for already completed actions, and if a compensation fails, we simply retry as many times as needed. But remember what I asked? What did we lose from ACID? Turns out, atomicity is completely gone. We may even have situations where our Saga wasn't successful, yet we are not back in the original state. On the other hand, we gain something else instead. And I'll get back to that in a second. Consistency might also be temporarily violated, but at least we still have eventual consistency. How about isolation? Well, not even close. Once we make a booking, that booking is visible to everyone else until we cancel it in case of a failed Saga. Finally, durability. That's actually the only thing that remains unchanged. Before we discuss what we gained instead of atomicity, let's pause and appreciate the real genius behind what my coach suggested at the time. Because we didn't just sacrifice one of the acid properties to boost availability. We fundamentally shifted our approach to building resilient systems. That's the power of having the right coach. They help you step back, see solutions clearly, and save you from years of trial and error. Whether I was leading a team for the first time, starting a business, or even learning how to work with my ADHD brain, the right coach has always made a huge difference for me. And now, as a coach myself, I help engineers and tech leaders tackle challenges like technical debt, system scalability, or effectively transitioning to microservices. If any of that resonates with you, I'm offering a limited number of free 30-minute consultations. Check out the link in the description and let's see if coaching is the right fit for you. Now, let's get back to what we gained in place of atomicity. The Saga guarantee ensures that either everything completes successfully or any completed actions are properly compensated. So far, this almost sounds like atomicity. The key difference is that instead of rolling everything back, we compensate for any undesired effects. Where this becomes significantly different from transactions is the third option. The Saga can be partially completed as long as we are still in the process of executing actions. That's all well and good, but you may run into one more issue. Not all actions can be compensated for. Sending an email with a VIP coupon is one of those hard to compensate for actions. For that reason, a variant of the Saga pattern allows for a forward recovery phase. After executing all compensatable actions, we can have a number of tasks with a different set of properties. These tasks need to be idempotent, and we need to be sure that they will eventually succeed after a number of retries. If the process fails during this forward recovery phase, instead of compensating, we keep retrying all remaining actions until they succeed. Now we know how the Saga pattern works, so it's time for us to dig deeper and learn how to actually build it. We will need two main concepts, the Saga log and the Saga execution coordinator, or SEC. The Saga log is a durable record of independent actions. It serves as a single source of truth, typically stored in a sharded database. The SEC, on the other hand, is a stateless and fungible process that processes Saga logs. It can fail and restart at any time. The Saga log typically starts with a list of tasks. Initially, the Saga execution coordinator reads the list of tasks and writes a single line, begin Saga, to the end of the Saga log. After that, the SEC writes begin task 1 to the Saga log and starts executing the first task. Once that is done, the SEC returns to the Saga log and writes end task 1. This continues with the remaining tasks until we complete the final task, at which point we write end Saga to the end of the Saga log. The more interesting case is what happens if the process fails, say at task 3. In that case, the next time an SEC picks up the Saga log, it will see begin task 3 at the end of the log. This tells us that task 3 has failed. At this point, the SEC writes abort Saga to the end of the Saga log and starts compensating actions. First, it needs to compensate for the last action, which was incomplete. That is because we don't know whether the failure happened before the communication with the external service or after it. After that, the SEC writes begin compensate task 3 to the log and proceeds to compensate for the action. This also highlights an important nuance. The Saga execution coordinator must be able to compensate for an action even if it was never successfully executed. Once it compensates for the failed task, the SEC will continue compensating for all previous tasks as well. If the SEC fails during a compensating action, the next SEC instance will continue compensating by retrying the last failed attempt. So when do we need to start compensating actions? Either when we find a Saga log that ends with the begin task operation, or when we find a Saga log that contains an abort Saga operation. The one exception to this rule is if we are already in the forward recovery phase of the Saga. In that case, instead of compensating, we keep retrying the remaining actions, extending the Saga log as if there were no failed attempts. Some actions are naturally idempotent, but when they are not, we need a way to make them idempotent. To do this, each Saga has a Saga ID, and within each Saga, every action has a unique action ID. On the receiving end, we can use these two identifiers to create a unique key for each action. These keys will be stored in an action ID registry. In the ideal case, when a request comes in, we start a transaction and attempt to insert the action ID into the registry using a unique key constraint. If the insert is successful, we execute the action. If the action succeeds, we commit the transaction and respond with OK. Alternatively, if we encounter a unique key violation, it means the action has already been performed, so we can safely return OK without executing it again. In all other error cases, we roll back the transaction and respond with a failure. At this point, you might be feeling a little overwhelmed, and that is completely normal. The Saga pattern involves a lot of moving parts, but don't worry, you don't have to remember everything right now. You can always come back and rewatch the detailed explanations later, or just leave your questions down below in the comments. I personally read and respond to as many as I can. For now, I just want you to remember two things. First, if you need to communicate with multiple services to achieve a complex workflow, think of the Saga pattern. You may not even need to build it yourself. There are ready-made frameworks that handle this for you. Second, if you're providing an API, guarantee idempotence on all endpoints. You never know when someone will need safe retries, and failing to support idempotency can make that impossible for them. Either way, I hope this video helped you avoid a mistake. We all make them. I have certainly made my fair share. If you want to learn more from my mistakes, watch this next video here, where I tell the short story of every single mistake I made throughout my career.